Imagine you got a new apartment and you have a box that you need to bring up. Well, this thing could be heavy and it's going to really cause you a sweat. But where are you taking this? Maybe you're just on the second floor. Or maybe you got to do more work and go up to the next floor above that. What else can cause you to do more work is what if it gets really heavy because it's filled with books versus maybe another box filled with feathers? This gives us the idea of work. And what is work? It depends on those two things: force, which is the amount of weight that we're carrying, and the distance that we're traveling up. And so what we need to think about is how can we combine both of these things so that way the amount of work we do encompasses this? Well, we can just multiply them, where work is equal to force times distance. And for the units, what we can think about is force measured in newtons and distance in meters, giving us the units of Newton meters.
So let's take a look at a few basic examples of how work is calculated. And we're going to start off really basic without any calculus. And then example 3, we're going to see why the calculus part of this becomes necessary in certain cases. So in example 1, it says how much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. So the first thing I want to point out here is what's given to us is 1.2 kilograms. That is a measure of mass. And the 0.7 is a measure of distance. So as we know, work is calculated by force times distance. So there's a couple things we have to recall from maybe a previous physics or math class that you've taken in the past. And that's, how do we know how much force there is? There was a formula that you might have come across that's force is equal to mass times acceleration. Or sometimes we'll write it as force equals m times g, where g is acceleration due to gravity. And there's a constant that we use for that, which is 9.8 meters per second squared. So if you're not familiar with those equations or those constants, those are things to kind of just review, take a look at, remember, because it comes back in different situations. And so let's look at this now. What was given to us is mass and distance, not force and distance. So we're going to have to apply this to be able to answer this question of how much work is done. So let's just plug it in really quick. We know that force is our mass times acceleration. So our mass is 1.2 kilograms. And for our acceleration due to gravity, right, that's the force it's putting down on us, is the 9.8 meters per second squared. And so multiplying this out will give us the total amount of force, which is 11.76 on my calculator. And the units would just be kilograms times meters per second squared. And there we go. There's the amount of force. Now, one thing I'll point out in case it's been a while, this kilogram meters per second squared, sometimes we like to simplify this into another units that they use in our international standard, where if we ever have kilogram meters per second squared, another way of writing this is we call them a Newton. So this is equivalent to 11.76 newtons, which is our units for force. So there we go. We have our force, 11.76 newtons. We have our distance. Let's just plug it directly into our formula. And this gives us 11.76 newtons times 0.7 meters. And putting this into our calculator gives us 8.232 Newton meters. Or just like here, how we have these complicated units that simplifies that we just call a Newton. When we have Newton meters, often what we'll just say is this is joules. We'll use the unit of joules, and I'll spell that out for you. And there we go. So this is our measure of work. Let's look at one more example here. So the first one we saw was using our international standard units of newtons, joules, and whatnot. But sometimes we're not using those units. Sometimes we're going to be using just the things that we use here in the US, like pounds and feet. And so that's okay as well. So in example 2, it says how much work is done in lifting a 20-pound weight. So one thing about weight is that's already a measure of force. Pounds is a measure of force. And then we have to lift it 6 feet off the ground. Well, since we have force and we have distance, we can go straight into our formula. Force times different distance is going to be 20 pounds times 6 feet. And this gives us 120. And what's our units here? Units here, pounds, foot, or often we'll just write it as foot-pounds. And it's okay to leave it as those units there when we're working in pounds and feet. So again, very straightforward on how to calculate the work. But now let's take a look at example 3, where it says, when a particle is located a distance of x feet from the origin, a force of x squared plus 2x pounds, so this here in pounds is our measure of force, and acts on it, how much work is done in moving it from x equals 1 to x equals 3. So here's our distance that we're looking at. And again, we're working in feet here. And so what we have is we can calculate, again, the work as force times distance. Now our force is a function, though. It's a function of x. So everything we've been doing before when we're looking at our force has always just been some constant. It's been 11.76 newtons or 20 pounds, where it's the same amount of force being applied the entire time. But here, that force is changing. Every single time I move my x, it's a different amount of force. So how can we do this when we are changing our force? Well, as soon as we hear things are changing over some x value or over some time or over some other variable, that's when calculus is going to start coming in handy. Because again, the idea of calculus is helping us do these calculations when there's things that are changing, constant change. So let's think about this. If we think of work, again, as force times distance, you may want to just be like, okay, let's just take our force function, which is x squared plus 2x, and then times some distance that we're moving in our x. And the way we say that, since we're changing some distance, we may just put like a delta x, meaning how far in the x did we move. Because what we want to do now is thinking about it in the same way. We're going to break this up into a lot of tiny little pieces. Rather than seeing how much is done overall like we did in example 1 and 2, we're going to be like, all right, if we were at x equals 1, how much work would it take to move a little bit? What about at x equals 1.1 or 1.01? How much work is going to be done on that? So we're just going to do it little bits at a time, where we're going to take every single piece of our force at a given x times the tiny little bit of x that we're going to move. And then when we have all these little bits of work that we do, we can just take it and add it all together and get the total amount of work done to move it this entire distance. Well, that should sound familiar. We're adding together, or taking the sum of a bunch of tiny parts of this, maybe at xi, we'll just say at any x, xi times 2xi. So whatever force we're doing at this point xi times the little amount that we're going to move there. And when we add these all together, this is going to give us the total amount of work. And of course, well, how big of an x are we moving? The idea is we can hopefully do this with an infinite number of delta x's. So if we do this at a infinite number of x points, this is like saying xi goes from 1 to n, but we want this as n goes to infinity. And now this should look very familiar to you from previously, where you learned about how this can just be written equivalently. It's the same calculation as taking the integral of x squared plus 2x times dx. And of course, we're going from the lower to the upper number. So the formulation of this using the what we call the Riemann sum, right, is just a reminder that our integral is just adding together all these little bits of forces times the little bits of distance. But the way we calculate it equivalently is by using the integral, using the antiderivative here. And in this case, what is our a and our b? I guess I should put that in here. Is we're going only between x going from 1 to 3. So there we go. Let's do this calculation, and we'll have the amount of work that we did. And if you notice, again, just when we're looking at it here, this represents our force, and the dx represents our distance. Oops. I'll write it as force. And this represents our distance. And so this calculation really is just the work calculation that we're doing. So let's do the formula here. If I were just to apply our power rule, we can just remember that we're just going to add 1 and then divide. So 2 plus 1 is equal to 3. So this gives me x to the third over 3. And then here, if I have a 1 already, we add 1, that gives us 2. So that would be plus 2x squared, and then that 2 we're going to divide by. And of course, this is a definite integral, so we're going to evaluate it from 1 to 3. And simplifying this a little bit, I just see these 2's cancel out, so I have x to the third over 3 plus x squared, evaluated from 1 to 3. Then of course, now we can just do the substitution. So we have, plugging in the 3 is 3 to the third over 3 plus 3 squared. Right, so I plugged in the 3 for the x's. Then minus, now we'll do the 1. 1 to the third over 3 plus 1 squared. And if we work this out, it'll give us our answer. And this comes out to about 50 over 3, or approximately 16.67. And if we remember our units, again, we're talking about foot-pounds. And so there's our answer. So we can see how the calculus, again, becomes important to us in order to calculate work when the force is changing. If it's constant, then we don't need calculus. We can just plug it in. But here, we can do this. And so, again, I showed you this Riemann sum formulation of it, but in the end, we can really just break it down to just a single formula. And this one right here, where we can just go straight into the integral, where our integral is going from a to b. And remember, it's just force times distance. And if our force is a function of x, we can write it as f of x, so f for force. And our distance, remember, is just the tiny bit of distance that we're going to move. So that would just be our dx. So this is how we can calculate force. And you're going to see all the different examples of this in the other videos and throughout the assignment. Good luck.